initial value problem where you have a huge bomb blast and you want to see how the system evolves, there's an exact solution of the Euler equations, which is due to this Taylor, von Neumann, and Sedov. This is from the around the time of the Second World War. Okay, 1945. This is a very old but very nice self-similar solution, exact solution of the Euler equations. And so I will talk a little bit about this solution. And then basically what I'll do is I'll present simulation results for a particular model. So we do microscopic simulations and ask how do these results for various observed quantities compare with what you get from this exact solution of the Euler equation. Okay, so this is the TVNS solution. So we'll compare what we get from microscopics with this Euler equation results. And we'll find that there's quite a very good agreement, except for in some deviations that one observes in the center of the blast. And this we will understand that you need to work beyond the Euler equation description, and then you have this Navier-Stokes equation. And then I'll describe again if we solve the Navier-Stokes equation and compare with how does it compare with the simulations. Okay, and then we will discuss the main results. So. So let me just keep track of time. Okay, so please interrupt at any point of time, because whatever I say should be accessible to, I mean, it should be possible to explain every detail. So if you have any questions, just ask. Okay. So this is the usual picture that in equilibrium statistical physics. So the microscopic description of a system is, let's say we are looking at systems in one dimension, and you have n particles so you need to specify the positions and moment of all the particles, and then something called Hamiltonian, which has the kinetic energy part and then a potential energy part. And then given this Hamiltonian, one can write the equations of motion. So qk dot is equal to pk by mk, and pk dot is equal to minus del h del qk. So this is basically Newton's equations. And basically the idea is that if you know the initial conditions, you know the entire trajectory at this microscopic level. But then when we come to the macroscopic description, then we realize that we don't care about these individual positions of all the atoms. And it turns out that good description is in terms of just a few extensive conserved variables. Okay, so for a typical system, let's say a gas in a room, the sort of important quantities are the total number of particles, the total volume of the room, the total energy of all the particles in the room, and the total momentum of all the particles. Okay, so these are the only sort of conserved quantities, and in the macroscopic description, somehow these are the only relevant variables. Okay, and the basic idea is due to Boltzmann and Gibbs, where you say that, okay, at a microscopic level, the system is evolving on a constant energy surface. And then for the macroscopic description, what you need is this area of this constant energy surface. Okay, so this I denote by omega. You integrate over all phase space, but restricted on this constant energy surface. That's the delta function. And once you know the area, then the entropy function is given by log of this omega. Okay, so this entropy is, let's say, a function of total energy, volume, and number of particles. And this is sufficient to, so once you know this entropy function, you can calculate all equilibrium properties of a system. For example, the equation of state, specific heat, compressibility, etc. Pretty much everything, all equilibrium properties you can compute. Okay, so it's quite a, I mean, if you think about it, it's quite a remarkable thing. And why it works, of course, is it's in some sense still it's still in some matter of constant discussion and research. Okay, but this is the for equilibrium systems, this is how we do things, and I think everyone knows this. Okay, so now when we come to systems out of equilibrium, so let's say consider gas flowing through a pipe or water boiling inside a beaker, or a cyclone, or even let's say supernova explosion. So then let's ask, what is a useful way to describe such a non-equilibrium system? And then the basic idea of hydrodynamics is that let's say, so supposing this, I have this picture of this gas inside this tube, which might be at different temperatures at two ends, or there might be a water flowing through this tube. Now, what we can do is we can break it up into these blocks of size L, which are sort of small but still contain a large number of particles. Okay, so this could be like maybe each L has 10,000 or 100,000 particles. So it's still, of course, short, quite small in relative to usual scales of observations, right? Okay, so now in this each of these cells, what we say is that you can define the system is in a state of local equilibrium, and then we know that to describe equilibrium, you need to describe the conserved quantity. So basically, in this small box, you count the number of particles, the total momentum of all the particles, and the total energy of the particles. And if we say that in this box is in a state of local equilibrium described by this observable. Okay, and then we say that this is not uniform everywhere. So so you have three fields which vary in space and in time. Okay, and so instead of N, P, and E, we can also talk of like equivalently density, velocity, and temperature fields. And these are really the observables that we really care about, right? If you think of water boiling in a beaker, you want to see how the velocity, how the flow is, and what is the temperature scale. So these are really the interesting observables. Okay, so now question is how do these fields evolve? And because they are conserved fields, it happens that they evolve very slowly both in space and time. Okay, and their equation is the equations of hydrodynamics, which I will write shortly. And so let me just go to the next slide. Okay, so now how do you so these fields, so there are three fields describing the system at a macroscopic scale, and here I say like how is the macroscopic and microscopic pictures, are how are they connected, right? So the density field, as I said, is the total number of particles in this small box divided by the size of the box, and equivalent way of writing this is putting this mass of every particle and then putting a delta function which says is the particle located at x, right? So this gives us the density. So from the microscopic description, this where we know all the positions, we know the density. Similarly, if you know all the velocities and the positions, then we can construct this momentum field and then the energy field. Okay, so this is how we go from the microscopic to the macroscopic descriptions. And now let us ask, what is the equations satisfied by the three fields? Okay, so these are the equations of motion for the hydrodynamic fields. And one point is that these equations of motion can be written down without really caring about the microscopic description. Okay, so these are basically this is what Euler and then this Navier and Stokes, they wrote around, I think, maybe 19th century or something. And they didn't really worry about where the microscopic model or underlying microscopic model. So they wrote these equations purely phenomenologically. And okay, so these are the three equations. So the first equation basically implies conservation of mass. So if you look at it, you see that it has the form of del rho del t plus divergence of rho u equal to 0. So rho u is the particle current density, right? So it's just a conservation of particle number. And the second equation has again the form of del del t of rho u plus divergence of something equal to 0. And it's conservation of momentum. And the last equation is conservation of energy. And this equation, it has two kinds of terms. Okay, so there's this time derivative terms, and then there's this divergence of something, and this terms on. So I've written certain terms in red. These are what are known as the dissipative terms. Okay, and so the first term is like if you have viscosity in a system, then it slows down the let's say the relative velocities between particles, and then you have this kappa, which corresponds to heat conduction. Okay, so these red terms are what I will call dissipative terms. If you drop these terms, then what you have is is called the Euler equations for a compressible fluid. Okay, and then in this equation there are some other terms. P is the pressure, and then there is this epsilon, which is basically the energy per unit mass. Okay, so now let me just talk a little bit about the pressure and this energy per unit mass. So this pressure is something which again you can.
Abhishek, I have one question.
Yeah.
So in the last term, what is that dissipative term? Eta u del u del x, last equation, right hand side.
Right. So this is it. U is of course the velocity field, but so it's the same term. But you can show that if you write it here, you need to write it here also. I mean, one way to see it is that if you require that this system has Galilean invariance, then you'll see that you automatically need this term here.
Okay, and in the first equation there is no diffusion, or I think you have ignored it probably.
No, so the first equation is supposed to be exact, and it doesn't have a diffusive correction.
Why?
Okay, so this I mean I can't write, but basically
Okay,
if you
maybe we can come back to it later.
right, so very quickly if you look at this definition now, if you take del rho del t here, okay, so in the first equation, then you will get something like mj qj dot. Okay, and that is already exactly it's like del x of p. Okay, so maybe I don't know if that's clear. So, but this first equation is supposed to be exact, and there's no diffusive corrections.
No, but macroscopically, if you see, I mean, particles they diffuse, right? Density field, particle will diffuse.
No, I mean okay. So of course, see, this is the fluid. I'm not talking about particles in a fluid. This is the fluid itself, and of course you will have it will flow and all, but they I mean the velocity field might diffuse at some in some approximation, but the density you don't expect it to show. Like if you just have water in a beaker, it won't just diffuse, right? It will just the density will remain constant. And if you create a perturbation,
microscopically, water molecules are diffusing, isn't it?
yeah, but this is at a different scale, right? I mean, you are not looking at a microscopic level. You have coarse grained, and in this coarse grained,
oh, I see. Your scale. No, so then I mean, in that scale, you have ignored the diffusion. That's the problem.
No, I mean, yeah, at this macroscopic level, there's no, I mean, you won't get diffusion. So I'm saying this first equation doesn't have a diffusive term. In principle, it could have.
It is exact. And
yeah, this is exact.
Okay.
Right. Yeah.
Okay.
I mean, yes. Right. Yeah. Okay. So, So now what I was saying is that if you drop this rate terms, then the equations that you will get are called Euler equations for a fluid. And if I include the rate terms, then I'll call them Navier-Stokes-Fourier equations, okay, or NSF. So I hope this is sort of this distinction is important. So please remember this. So without the dissipative rate terms, it's Euler equations. If I include them, it's Navier-Stokes. Okay, so now there are these three independent fields, rho, u, and t. That's where so you can see rho here, u here, and okay. So where is temperature? So now this epsilon, I said it's the energy per unit mass, and this you can break it up into a flow energy because the fluid is moving. So there's a sort of advective energy, which is the kinetic energy of flow, and then there is an internal energy. Okay, so you can break it up into these two parts, and the internal energy would depend because this is you assume local equilibrium. This will depend on the density and temperature. Okay, so this is from equilibrium physics. You know this, and similarly there's a pressure term, and this pressure again is just from the equation of state. You know it as a function of rho and t. Okay, so finally there are three independent fields rho, u, t in this equation. And these equations are basically expect to, tell us how water flows in a tube, or what happens in if you have a free expansion of gas or whatever, right? So these are the hydrodynamic equations. Okay, so this I already said. I mean, you should note that all these equations have the form of local conservation laws, and they correspond to conservation of particle, conservation of momentum, and conservation of energy. And okay, so then I said that this currents, momentum current, has what are known as reversible and irreversible parts. So parts involving heat conduction are the irreversible parts of the energy current. Okay, and okay, so that's one distinction. And then other point I want to make is, when I say dissipation, it basically means transfer of energy from the hydrodynamic fields to the internal degrees. Okay, so the entire system is completely a conservative system, which has total energy is exactly preserved. But when I say dissipation, it just means, like, for example, if you stir a fluid in a beaker, after some time you see that the flow stops. So where does the energy of this kinetic energy of flow go? It basically goes into heating the fluid a bit, maybe, right? So this is what I will refer to as dissipation. Okay, and apart from that, there is some connection to microscopics, in that I need to, for example, this functions internal energy as a function of density and temperature and pressure. These are can be obtained from equilibrium statistical physics. And then there are these two transport coefficients, the viscosity and thermal conductivity, which in principle can be obtained from linear response theory or Green-Kubo formula. Okay, so I hope this description.
Sorry, Vishal, I have another query.
Right, yeah.
No, so when you say stir a liquid, so then the actually momentum is getting transferred to the environment because it is in contact with some wall, right? I mean, if it's strictly conserved, then it will keep on rotating.
Okay, so let me see. I mean, okay, I mean, that is true. I mean, probably, like, yeah, total momentum. No. So what I'm saying is, let's say, no, okay. So imagine, like, you have some fluid where, okay, so total momentum is of course conserved, but here when I'm stirring, what I'm generating is relative motion, right?
Yes, I mean momentum is being transferred from one part to another.
Yeah, so my momentum is okay, but you can imagine, like, even if I didn't have walls, okay, so let's say, okay, I mean, I don't know how to do this, but okay, without walls, of course.
No, yeah, I mean, you can construct frictionless wall, for example. I mean, that's possible.
Yeah, so even that I'm saying, like, eventually this relative motion between this, so you have a flow velocity, the flow will eventually stop, right? So even without wall, I can imagine the relative whatever motion you have in the fluid, that will eventually stop. It can't keep moving unless it's a superfluid.
Yes, no, that's true. Yeah, that's true. But
the stoppage happens because of the dissipation. Without dissipation, the momentum will always be there, so it will always move.
No, I mean, no dissipation. I mean, I'm saying
the stop
here,
stops because of the dissipation term.
Yeah. So it's
term
viscosity term, but I'm saying this viscosity term doesn't mean that. See, at the microscopic level, I said we have a completely system of particles which are following Newton's equation, right? And this dissipation also came from the same Newton's equation. So finally, this total energy is completely conserved. What you see as like the viscosity and the heat conduction term, we are calling them dissipative terms, but it just refers to transfer of energy from these macroscopic fields to internal degrees.
Yes.
Right. Okay. So this is all I'm saying. Because finally, if you think about it, I mean, finally, it's a completely conservative system, right? I mean, there's no loss of energy. It's if you think of the microscopic picture, like you have set of particles following Newton's equation.
No loss of energy, probably that means no loss of momentum too.
Yeah, no loss of momentum too. Of course, if you have walls, there's always loss of momentum, but I think that wall is not so important. So in principle, there's no loss of momentum.
Okay. No, the relative motion will stop, but say for example, rotating fluid, I mean, up to a frame of reference, like that rotating frame.
Yeah.
I mean, because angular momentum also will be conserved. Angular momentum also will be conserved.
Right. Yeah.
Yeah. So relative
Here,
that frame probably.
what is really relevant is the relative motion. I mean, so let's not think of
right. No, that is correct. That's true.
Yeah. So maybe that's a easier thing.
Yeah, I agree. Yeah, that I agree. Okay, thanks.
Okay. So now I hope this hydrodynamic description is clear. Okay. So now some questions are: is there a rigorous derivation of hydrodynamics from Newton's equation? So this is in fact kind of part of Hilbert's sixth problem, and so far it's not solved. But I mean, from a physicist point of view, I mean, there's some progress. Like if you start from Boltzmann theory, and there's some systematic expansion that you can do and to derive the equations of hydrodynamics. Okay, so it's not completely microscopic because you have to start from Boltzmann theory, which already is approximation. Okay, so so I just want to say there's no really complete, rigorous, or even at a physicist level derivation of this equations. Now, one other question that we want to ask is how accurate is this hydrodynamic description, and where are there situations where it might break down? And surprisingly, there are not many precise numerical verifications of this equivalence in a precise way. And this is exactly what we want to do here. Okay, and what we'll study is this blast wave problem, which is an sort of, I mean, it's like I said, it's like looking at a bomb blast. It's an extreme example where you might think that you have sharp fronts and discontinuities, so maybe the hydrodynamic description might break down, right? So this is what we want to look at. Okay, so now
No, sorry. What is the reason you expect?
No, so if you blast, I mean, sorry. So in a blast,
what is the reason you expect?
So we expect that the hydrodynamic description might break down because this blast problem involves, as we will see now, like sharp discontinuities in these fields, and so it's natural to expect that there should be some problems in a continuum description, right? And it's an extreme situation. Like it's not. You might expect things to be not so smooth and so on, because we assume local equilibrium.
Oh, local equilibrium. Okay.
Local equilibrium. That is, of course, one strong assumption, and this is looks like a very violent thing, right? So naively one expects that this might be some problem. Okay.
Local equilibrium might break. Yes.
Right. Yeah. Okay. So let me just give some history of this blast problem, which is actually very interesting. So this was first studied around the time of this atom bomb explosion, and this Trinity atom bomb explosion is the first test that the people did at Los Alamos to see whether this works or not. This atom bomb, and this is done in 1945. And this picture you see on the left hand side, it is this explosion after 16 milliseconds. What the explosion looks like. Okay, so after 16 milliseconds, extremely small time, it's already 200 meters in diameter. And on the right hand side, you can see how this blast is evolving in time. Okay, so it started small thing. After some time, I think this is after every 0.14 millisecond, these frames. You see that there's a sharp front which is growing with time, right? Okay, and so basically this explosion creates a region of intense activity and high temperature, and there's a sharp shock front which grows with time. And so one question is, how does this shock grow in time? That's the simplest question one can ask. Okay, so let's first answer this question: how does the shock grow with time? And this actually you can find and you can answer this question quite, I mean in a very simple way, and it's amazing how it works. Okay, so this is basically doing dimensional analysis. Okay, so I mean, given the shock, we want to know what is this radius. So that is the length scale, right? R of t. At time t, what is the size? And then if we think about it, what can it depend on? It can depend on the initial energy that was released in this explosion, and it can and the shock is expanding out into some ambient atmosphere, which is, let's say, at some density rho, which I call rho infinity. Okay, so there's this energy E, which is the total energy of the explosion, and then there's the density of air into which it's expanding, and then there's time. So these are the only things it can depend on. And then you said, let's say you just do usual dimensional analysis, put radius is e to the power a, rho to the power b, and t to the power c, and then equate both sides for dimensions. Okay, if you do this, you get so you can compute ABC uniquely, and you get this nice simple formula. So radius depends on E times t square divided by A is some dimensionless constant times rho infinity, which is the density of air, and to the power 1 over d plus 2. Okay, and so d is the dimension. You can do it in any dimensions. And okay, so this is the basic formula. So in d equal to 3 dimensions, if we put, then we get RT grows as time to the power 2/5. Okay, so it's a sub-ballistic growth. So naively, one might think that it should expand ballistically, but it is much slower than that. It grows as t to the power 2/5. Okay, and on then like we can ask how well does it fit what we see in these plots, and so people extracted this length scale as a function of time, and so this is actually what is plotted here is 5/2 log of r. So if you take this log of this equation, you get 5/2 log of r is grows as log of t, right, with some constant, which is this. That's the slope. So so you find that this fits perfectly to this formula. Okay, and and from this you can estimate what is the energy released in this blast, and it turns out that you get this number 10 to the power 14 joules, which in fact is one of the best estimates of the amount of energy that was released in this explosion. Okay, so it's quite amazing that this simple analysis gives you such, good fit to what you observe experimentally.
But
okay,
is
so
it still slower than diffusion?
it is slower than diffusion. Yeah.
Yeah, that's a bit strange.
Okay, so I mean, this is exactly the question that Christian Mays asked me yesterday. He said he would have expected diffusion, but you don't expect diffusion.
Yeah,
because,
right.
Right, yeah, because so if you use the diffusion equation, of course, to see how energy spreads, then of course you would get t to the half. But the point is that in this case,
Right.
the temperature actually couples to the velocity field and the density field, and you have to solve all these equations together. And so you don't. So just the diffusion equation is not enough to predict this growth.
Okay, that's interesting. Okay, thank you.
Right. Yeah. So I just as another example, I mean, these equations are, and this formula that I just wrote here, this is also used to, for example, analyze what happens when in a something like a supernova explosion. Okay. So so this is a real picture of this Crab Nebula at present times, and so we know roughly when it exploded, and then so now you know its size, the radius, and you know the time. So from using that formula, you can estimate like, for example, how much energy was released, and you can also, quite amazingly, you can find the speed at which this front of the nebula is expanding. See, this formula it doesn't involve any other parameters. Okay, it's just 2/5 of r by t, and we know r and t, and we get this number 1250 meters per second. And it's quite this is what people believe, that this is the speed at which this is growing. Okay, so these are just some examples where this kind of results are used. Okay, so now I will come back to our more detailed question. So we have this blast, and we know how the front is expanding, but we want to know, like, what do these three fields, what is the profile of density, velocity, and temperature inside this blast? Right? That's the That is the more detailed question we want to ask. Like, is the temperature maximum at the center? Is it maximum at the edge? So this, I mean, it's difficult to guess, right? I mean, if you think about it, I mean, we don't know. I mean, so density, is it maximum at the center or at the edge of the shock? So this is what we want to find. And what one can do is solve the Euler equations. And okay, so, and this is what these people, Taylor, von Neumann, and Sedov obtained. So they could solve these equations in any dimension. So there's an exact scaling solution, and this is what I'll just describe. Okay, so this is what is called the TVNS scaling solution. So let me just talk about this now. Okay, so these are the Euler equations, and we just stick to one dimension right now. So these are the Euler equations where I have dropped the dissipative terms, and I also assume that my system is an ideal gas. So I use the equilibrium equation of state, pressure equals to n kBT, and also the equilibrium, the ideal gas energy equation, right? So it's just kBT by 2. Okay, so now the shock position we already know. So in 3 dimension it was 2 over 5. In 1 dimension it's t to the power 2/3. Okay, and this a constant a can also be determined exactly. Now what TVN has found is that like I said, there's a scaling solution of which has this form. Okay, so rho depends on x and t through this combination x over RT, and then there's the scaling function g, so g of z, and then there's some prefactor. The velocity, we can pull out some dimensional thing like which has dimensions of velocity, but then there's a scaling function which depends on the same scaling variable z, and similarly temperature. Okay, so now we can, if we assume that there's such a scaling form, we can use this and plug it back into the 3 Euler equations which I just wrote. So now so you can imagine that this del t and del x can both be written in terms of del z, right? So instead of partial differential equations, we get 3 ordinary differential equations where there are derivatives with respect to z. Okay, so those are the, so now this if this scaling solution holds, then we have this simpler description of just 3 ordinary differential equations. And now there's we know there's a shock front, and then in hydrodynamics, this is one can determine something called this Rankine-Huguenot boundary conditions, which again basically follows from these equations. Okay, so because there's a discontinuity, you need to sort of take an integral of these equations across the shock, and this gives rise to some boundary conditions, which so on the right of the shock, it's the temperature is 0, pressure is 0, and velocity field is 0, and the density is this rho infinity. And on the left of the shock, it's given by these values, rho of r, v of r, and so on. Right, so these are some boundary conditions. Okay, so we have set of ordinary differential equations with some boundary conditions, and then there is this also, of course, this condition of energy conservation. And using this, we can. So it turns out that once you write these ordinary differential equations, you can actually solve these equations exactly and find this g, v, and z, the scaling function. Okay, so I won't go into the details, but one of the tricks is that you change from this z variable to the new variable L, and then write this ordinary differential equations in variable L, which can be solved. I mean, this is quite miraculous that you can solve these complicated equations, but somehow you can solve, and I just write the solutions. Okay, so you can see that this first equation, for example, it's you can invert it in like numerically, of course, and find v as a function of z. Then the second equation then gives us the z, and then you can also obtain g. Okay, so if we go back to our solution, we know all the scaling functions g, v, and z exactly. Okay, so we know how exactly the 3 hydrodynamic fields evolve with time, and this, of course, is at long times. Okay, so the scaling solution holds at long times. Okay, so I hope, is there any question? Is this clear?
Yeah, so what is capital E?
Okay, so that was the total energy that I put in the initial shock, right? That just depends on the initial condition.
Okay.
So the only parameters in this model are capital E and rho infinity.
Okay, right.
And I am assuming that the outside gas is at 0 temperature, because anyway the inside is so hot that I don't care. So I make the assumption that it's at 0 temperature, and there's no flow initially, and this is all right. So that's the complete description of the initial condition, and E and rho infinity are the only parameters in the model.
But then what determines the jump?
So the jump is, of course, you're saying at the boundary.
Right. Yeah, shock at the shock.
At the shock. Okay, so the shock, so basically this energy and rho infinity, that will eventually determine the size of the jump. So you have to solve, of course, the equation. This is kind of a boundary condition, the boundary condition at the shock. And then if you solve the full equation, then you get the exact values of at the jump.
Okay.
Okay. So so now what I'll talk about is so these are some references for like this kind of shock problems. So the best reference I would say is just Landau-Lifshitz, but these other problem books are also very interesting. They discuss a lot of scaling ideas. Okay, so now we have the hydrodynamic solution, exact solution of the Euler equations, and we want to compare with microscopics. And so let me just talk a little bit about some earlier work which tries to make this comparison, right, of TVNS with microscopics. Okay, so I think one of the earliest paper is this paper by Antal Kapivsky and Sid Redner in 2008, where, so the system is hard spheres in 2 dimensions. So just imagine at time 0, you have a large number of disks uniformly distributed on the plane, which are all at rest. Okay, so it's just uniformly distributed hard spheres. Now at time 0, you just hit one of the balls at the center, and so as you can imagine, it's like a carom board, right? You hit just one ball at the center, and then you ask some more balls get excited, some more balls get excited. How does this spread? So this is exactly like the explosion. Okay, and what they observed is this picture that I show here, it's what you see after a long time, and the red balls are all the balls that have got excited after some time. Right? Initially, only one ball was excited, and then it grows with time. So you can see this is this is what I would call a shock of size, some radius. Okay, the other thing you see is that, of course, there's a density profile right at the center. The density is kind of lower than the edges. So, and of course, there should be some velocity and so on. But this paper, they basically looked at the question at how does the number of particles, excited particles, grow with time. And they found that so if R is the size of the shock, you expect this to be R to the power D in D dimensions. And from the earlier solution, we expect that R goes as 2 over D plus 2. So this gives, this is what we expect. And they verified that this is indeed correct. Okay, so this is kind of like a check of between microscopics and hydrodynamics at some level. At least the size of the front, it's correctly what you get from this microscopic model is the same as this. Okay, okay, and okay, and then there's this paper from the people at IMSC, where they studied the same problem, but they also compared the case where this sphere collisions are inelastic. And in this case, if it's inelastic, then it's this picture on the left-hand side, and the picture on the right-hand side is for elastic collisions. Okay, so you can see it's very different. And the scaling of n is also, it's slower than what you obtain for the elastic collisions. But the other thing is, if we just focus on the elastic case, you see that it's a perfect sphere. Maybe because it's on a larger scale, there are, so in this simulation you see some fluctuations at the edges, but here it's much less because it's now on a longer scale. So you don't see the small fluctuations. And they, in this case, you would again see exactly what hydrodynamics predicts. And now you can ask, if you look at the density profile, does it agree with what hydrodynamics tells you? Okay, so this comparison of looking at the fields in this system was done by in this paper, this set of papers by Barbier et al. And then so there's some set of papers by Rajesh et al. Where they did a very detailed microscopic simulations using hard spheres in both 2 and 3 dimensions, and made a detailed comparison of the TVNS equation. Okay, and one of their main conclusions was there seems to be significant deviations between the microscopic and macroscopic results. Okay, so in fact, Rajesh gave a talk at ICTS, and that's how I got excited about this problem. And what we wanted to see is what happens in 1 dimension. Okay, so let me say why 1 dimension. So we basically look at a 1-dimensional gas of hard point particles. And the main advantages are compared to a hard sphere system in higher dimension is that for hard spheres, you don't know the equation of state, because for that you need a virial expansion and so on. But for this 1D case where you look at point particles, you know the equation of state is just the ideal gas equation of state. Okay, and then you can solve these TVNS equations exactly, which is what I just described. And also it's much easier to do simulations. Okay, so we hope that some of the problems in the higher dimensions will be avoided in this low dimensional system. And so now let me present the results. Okay, so this is the precise microscopic model. So we have point particles, which are colored red and blue on the line. And so we sprinkle them uniformly on this, let's say, line with some density, which is rho infinity. Okay, so they are uniformly distributed. And we take the masses of the particles to be different. Okay, so the red particles have some mass m1 and the blue particles have m2. The reason is that if you take equal masses, then the system is integrable, and it won't reach thermal equilibrium. Okay, so it's a bad system if you take equal masses. If you take unequal masses, then it's known to be strongly mixing and thermalizes very fast. And the dynamics is that they move freely, and when they collide, they just rebounce with some velocities, and which you can find just by using momentum and energy conservation, and that's given in this line here. Okay. So the dynamics is very simple. It's just ballistic motion and elastic collisions. And then the initial condition, we want to create this blast, which we do by saying that in a small box of size, let's say sigma, which is the initial each particle, and give it a momentum chosen from some Maxwell distribution at temperature T. Okay. So we set the initial temperature of all these particles to be some like very high temperature, and give them some random momentum in some directions. And okay, so this is a small number of particles at the center. And now we just let it evolve this system following Newton's equations, and we see how do the fields evolve. Okay, so this is what, if you plot the space-time trajectories of all the particles as a function of time, this is what it looks like. So at time, so y-axis is time and x-axis is space. At time t equal to 0, I'm plotting only the particles which are excited, right? So at time 0, all the particles are at rest except a small set of particles at the center, and then they start moving and they hit the boundary, and then this boundary evolves, right? So so you have a growing shock profile, and the dashed line here is actually the exact prediction from the hydrodynamic theory. And you can basically see that there are just some small fluctuations around this average profile, but more or less the system sticks to the hydrodynamic prediction. Okay, so then now the more detailed question is what do these profiles look like, the density, momentum, and energy. And this we can just compute from this. So we can take these averages and find these profiles. And I show you this again, these heat maps, which show you how these profiles evolve with time. Okay, so let's look at this first plot. So this tells us at time 0, we have some like it was uniform distribution of density. But after some time, what we see is that the density is highest at the edges and it's very low at the center, right? So black means it's a low density, and at the edge, it's the highest density. If you look at the velocity, it's highest at the edges, and again, it's very low at the center. On the other hand, for temperature, we see it's very hot at the center, and it gets there's some profile. It gets cooler at the sides. Okay, so these are the three fields. Now we can plot them and ask: do they? We have an exact solution from hydrodynamics. How does it compare? Okay, so here I plot the three fields rho, v, and t at different. So this is a function of x at different times. So the green curve is at time 10 to the power 4, and then it's 2 into 10 to the power 4, 3 into 10 to the power 4, 4 into 10 to the power 4. So we can see, like I said, there's a sharp shock front. Density is maximum at the center, lowest at the maximum at the shock front, and minimum at the center. And similarly, we see things for the temperature and velocity. And now we know that we expect a scaling solution. So if we scale x by t to the power 2/3, which is this variable z, then we expect a collapse, and we see that indeed you get a perfect collapse of the data. Okay, so for all three fields, you get a perfect collapse. And let me just blow this up a bit so that supposing you just look at the if you look at the temperature, what you can see is that the dashed line here is the exact solution from theory, and the simulations, this green is at an earlier time, and that as you go later times, you can see that both at the shock front, at the center, it seems to get better, right? It approaches the analytic result more and more at larger times. So we expect the scaling solution to be good, of course, at large times, and we can see this. But at the center, there's actually some problem. So now the main summary from this plot is that the TVNS scaling solution agrees with molecular dynamics simulation almost perfectly, except at the center where we see some deviations. Okay. So in particular, if you look at the temperature profile, you'll see that, so it's known that the exact solution has a divergence. The temperature field actually diverges. Okay, but the real physical field, of course, doesn't diverge. So in this case, there is some problem. Okay, so this won't, even if you go for longer times, this is not going to agree. Okay, so now what is the reason for this disagreement? Okay, so so like I said, this perfect agreement between simulations and Euler prediction, except in the blast score. And now we want to look at the full Navier-Stokes equation, and we had dropped these terms, the red terms, and we now ask: are these actually important, right? Were we correct in dropping these terms? So then a quick way to check that is to take the solution that the exact solution that we have, and then we just plug it into these red terms, and we compare their values with what we have on the left hand side, right? So if we find that, so this is kind of like a self-consistency check. We have dropped some terms, but now from the solution we ask, was it right? So if we take this ratio, say this is what I'm doing out here. So we look at the ratio of this heat conduction term to some term on the left. Okay, so just a time derivative of T by rho. So once we do this, using the exact known solution, we find that this ratio is given by, it depends on time and space in this way. Okay. And so this you can work out analytically. These factors look, these numbers look strange, but this just comes out. This is what you get. So now this ratio is large if x is less than this 38 by 93. Okay. So which means that so the entire blast is over a length scale to the power 2/3, and this is some much smaller length scale 38 by 93. So in most of the region, these red terms are not important, so we were correct in ignoring them. But in the center core region, it was not right, right? So we should have included the heat conduction term. Okay, so if we do this, then of course we have to solve these full equations now, and that there's no known exact solution. This you have to solve numerically, and so this is what we did, and so this is what I know is this numerical solution of the Navier-Stokes equations. So let me just look at time. Purnabrata, can I take like 5-10 minutes more?
Yeah, you have in principle 5 minutes, but I think you can take more.
Okay. Right. Yeah. So yeah, I think I'll finish by 5 minutes. Okay.
Yeah,
So
7-8 minutes is okay.
okay. Okay. So this is what we get from the full solution, and you can again see that this fields rho, v, and t they look very similar to what we had got from the microscopic simulations. But let us compare with the solution of the Euler equations, and again we see that if you look at the temperature, then the colored lines are what you get from Navier-Stokes. The dashed line is from Euler. So the Navier-Stokes has now got rid of the divergence that was there in the Euler equations. So at least that sort of artifact of the Euler equation is now avoided. So the Navier-Stokes equation with dissipation terms is certainly doing better at capturing the microscopic simulation. Right now, we can do a direct comparison of Navier-Stokes with the microscopic simulation, and this is what I show here. So here you can see all three methods. Red curve is microscopic simulation, blue curve is Navier-Stokes, and the dashed line is Euler. So you can see the Navier-Stokes is now doing better. So in most of the region, all three theories agree perfectly well. In this core region, which is much smaller than the most of the shock, in this core region, there's you see differences between Navier-Stokes and the exact solution. Okay, so okay, so this is the main conclusion, and so now basically that means there are two scaling regimes. One is outside the core where we have this Euler scaling, and inside the core we have a different scaling. And in this region, actually, we can find that this is this is how things the field scale with this is the scaling solution. So this is a completely different scaling solution than in the bulk region, and we can verify that both the microscopic and the Navier-Stokes actually satisfy this. So we get a collapse of data if you use these scaling variables, and but the scaling functions do not agree between microscopics and Navier-Stokes. Okay, so this is sort of still unsolved problem. Okay, and this is just one plot where I show that. Okay, so here when I showed all these plots, one thing we do is we did do an ensemble average, and this ensemble is over initial conditions which are chosen to all satisfy the initial condition of this blast. Okay, but at microscopic level we have a large number of initial conditions. So now one question is, of course, that when we observe a real system, we do not look at ensembles, right? We just look at one realization of a system. We never observe ensembles. So if we look at a single realization, then what one computes is something called an empirical density. And you can ask, does this also match with if you take an ensemble average? And in this case, we find that it agrees extremely well. Okay, so here I plot the ensemble average, and the colored things are what one gets from the single realization. You see more noise, so that's why it's better to do the ensemble average. But even the empirical density follows the hydrodynamic laws perfectly. Okay, so a single realization of a microscopic model, if you do coarse graining in space, that's how you create hydrodynamic variables that follows Euler equations very accurately. Okay, so I think that's that's more or less what I had to say. So basically what I tried to say is that there are two descriptions for the air in the room. There, of course, we know that there's an atomistic description in terms of the Newton's equations and so on, and then there's a continuum description of hydrodynamics. And the question we ask is this description always valid? And we tested this for the evolution of a blast wave. And we considered this particularly simple case of a one-dimensional ideal gas, which is a good model to use because it has exact solution of the Euler equation. It's easy to simulate because it thermalizes very fast, in fact. And we find a remarkable agreement between simulations and predictions from Euler. And then there are some small deviations that we observe, which also we partly understand, not completely yet. And so this is still an open question. Can we get perfect agreement between microscopics and macroscopics? And the main difficulty here is that these transport coefficients, which we should derive from microscopics, and in principle, they are supposed to be given by these Green-Kubo formulas, but they are not really known so well. Okay, and in fact, as Purnobroto said in the beginning, one of the problems in one dimension is that the thermal conductivity is in fact supposed to be diverged in one-dimensional systems. Okay, so in some systems, to writing this hydrodynamic equations itself is a bit tricky, and it's quite amazing that in spite of that, this description works so well in capturing what we see in microscopic models. So, so these are again, there are two papers that we have that are there in the archive right now. Thanks.
Okay. Thanks, Abhishek Dhar, for nice talk.
Hello.
So, any question maybe? You can take some more questions.
Please, Abhishek. Yeah.
Yeah.
Yeah. Actually, I'm actually a little curious to know about this. The approximate hydrodynamic description is there in terms of some kind of central force kind of thing is coming but maybe in the central region it is more central or than outside. And I am actually curious to know what are the scaling laws in the central region and in the outside region.
Right. Yeah. So there's a different scaling solution in the central region and outside region, and the reason is that in the central region, you have to worry about the fact that there's because the temperature becomes so high that you really have to worry about this heat conduction process and so on. So that these dissipation terms really become important in this core region, and so that's why you have a different scaling solution.
Yeah, but what are the values like if I want to have a description, a central force like description, of course this is not a continuous thing, it is impulsive force. But if I want to have a description like some nonlinear radius kind of thing in the steady state, not steady state. Anyway, just the scaling laws in the central region and the outside. What are the values?
So the outer solution
in three dimension.
So in 3 dimension, I mean this question of different scaling laws, it's not so well investigated. I mean, I think there is in that book by Zeldovich, there is some brief discussion, but it's not so well known. Like what are the different scaling forms in the two regions?
Anyway, okay, thank you.
Okay, Abhishek, I have a related question. I mean, if the transport coefficient like conductivity diverges, then how do you construct the Navier-Stokes equation? I mean, in I don't know, numerically integrating probably.
No. So in the okay, so in the simulation, of course, we just put some finite values.
Right.
Right. So that's why, of course, it's not agreeing perfectly, right? So this, of course, it's a very tricky issue. Like, what is the correct thing to put? I mean, there's some idea that it should be some non-local equation and so on, but it's not. But this is, for example, even in if you look at fluctuating hydrodynamics, there you put this bare transport coefficients, right, which includes thermal conductivity. But finally, we know that it leads to infinite thermal conductivity. So in some sense, one expects that maybe this is some bare coefficient, and then it will. So it's not. It's a bit hazy. I mean, it's not clear what is the right thing to do.
Right. But in principle, you expect that transport coefficient diverges.
If you use, for example, Green-Kubo, you'll get a divergent answer.
Right. Okay.
So probably you should use a non-local equation with some, but it's completely unknown.
Yeah. Okay. Maybe some other questions. Anybody has?
Yeah, I'd like to ask a question, Abhishek.
Yeah.
So when you compare with the this hydrodynamic equation from simulation, so did you look at the finite size effects? Because in the end, you have to go to the thermodynamic limit, right?
Right. So see here the system is it's a gas expanding, and there's no. So it's like you can imagine it's an infinite system, and as long as the shock doesn't hit the boundary, you don't really care about finite size effect. But the only thing is you care about is whether you have gone to sufficiently long times to reach the whether you have reached the asymptotics or not.
If you wait sufficient long time,
then
it should be close to the boundary, right?
Yeah, but we always we make sure that we don't hit the boundary, right? Because the solution is for the case where the boundary is at hit.
Okay, so you select the time window so that you don't really, hit the boundary. That's what
we never hit the boundary. Yeah.
And is it? Do you think that this similar kind of trick should work for the higher dimension also?
Similar kind of So in the higher dimension also, when people do,
I mean, the way that you have developed this scheme in 1D, should this hold for 2D and 3D so that you have an alternative to lattice Boltzmann type of description?
You are saying so you're saying like as a model for hydrodynamics, if we use particles.
Yeah. Like for example, colloidal suspension in a colloidal film. So can you use similar kind of description for such systems?
Yeah. So this will work in higher dimensions also. But in higher dimensions, at least so far, people have not been able to get a good agreement between microscopics and.
So that's the reason I'm raising this question. Okay.
Right. Yeah, but I think this I'm a bit surprising because normally you expect 1D to be most difficult, and higher dimension I would expect should be.
Yeah, but that's difficulty due to the divergence, etc., that you already talked about.
Right. Yeah.
For higher dimension, there is no divergence per se. Most of the cases
is being
so you taken care of. But the difficulty is in the actual. Yeah, setting the laws itself, right?
Yeah.
Like how do you get the hydrodynamic limit? That becomes a problem.
Yeah, that's a good point. Yeah.
But if you if you just take the hydrodynamic equations as they're given.
Yes.
Right, and then you know everything from microscopics, like the thermal conductivity and equation of state. Let's say you know this for a hard sphere system. Then the question is, will it agree? The microscopic simulations will agree with what you. But from the hydrodynamics, you can always make a prediction. Given
but I don't know whether any systematic. So I don't think any systematic has been done in this way.
No, this is what this Rajesh and all did in IMSC.
Okay.
But they didn't get a good agreement. Right, in 2 and 3 dimensions, this is what they did. But they didn't really get a perfect, they didn't get they saw some significant deviations.
I see.
Okay, maybe we move on to the next question.
Hello, sir.
So any more questions from the audience, especially the students?
Hello, sir. I have a question.
Yeah.
Sir, could you please move to the previous slide?
This or before?
The before one, where the density profile is plotted, rho xt versus x.
This.
The previous one, maybe. Mm,
This is density versus time, x.
it is still not loaded actually.
Oh, okay.
Oh yes, slides are not changing. Yeah.
Has it come now?
No, sir.
No.
Oh.
Okay, maybe Dheeraj, you can briefly describe what you saw and then. We can't remember.
Sir, in the rho xt versus x plot, there at the x equals to 0 point,
Yeah.
maybe for maybe I can see that there is some differences in slope, like the slope is abruptly changes while moving towards or around x equals to 0. So is there any specific reason for that?
The slope is changing with time.
Around, yeah.
No, I think not time. Probably as a function of x, slope has changed. I mean, I can't see the slide. That's the question.
Yes, as a function of x. That's the question.
The slope, okay. I mean, so the density. I mean, the density is almost changing linearly at the center. It's minimum, and at the shock front, it's maximum. And in between, it has some profile. Okay, it's changing more or less linearly with space. But I mean, this is what you get. I mean, so what is the question? I mean, why?
Yeah.
Unfortunately, we can't see the slides.
Oh, okay. I don't know what's happening. You can't see any slides, is it?
No, it has not loaded yet.
No, sir. We can see the slide in simulation results.
Yeah, I can see the slides.
Okay, I think it depends on your connection.
Yeah, right.
Right.
Yeah. Okay, maybe we move on to the next question. Another one or two quick questions. Okay, if there are none, so then let us thank the speaker again for his nice, insightful talk. So thanks, Abhishek Dhar.
Thanks a lot for yeah.
Yeah, thank you very much.
Okay, bye.
Okay, bye.
Okay, sir. I'm stopping the recording.